Okay, thank you again for coming, and thanks for the new people joining us. This is the second session on this topic of this semester on machine learning and data streams. In principle, we want to talk about data literacy, as we discussed last week in details. So, as I told you, the approach that I take, and I think this is, in my opinion, the best way, because you are all majority are architects and designers. You don't have this background in computer science necessarily. So I think the best way that this might work for you would be to think about it like I call it a wiki-based approach, that you need to learn and get familiar with a lot of keywords, and then think about it like a new kind of language, if it's not too much. Then, in principle, after a while, I think if you participate in discussions and attend and get engaged in one project, in this kind of data-driven project, I think you will realize that, oops, okay, now it's like I understand what's going on. And otherwise, the other way would be to just think about it like a very pedagogical. So you need to take a computer science bachelor degree and then a lot of courses and so on. So what I'm going to talk to you today is, I would say, it can be in principle opened into 3 courses, in chaos theory and one in probability theory, statistics, and fortunately or unfortunately, I took these courses because I was from a different background. But what I'm going to talk today is like very dense, and I'm just going to talk about different kind of keywords. So would be very great if you just stop me and ask questions if you don't like some part, or if you find some questions or something like that. So this is the main frame that I told you. This is somehow my image or my picture. It's not necessarily something like it's not there is no truth in this. Like, this is just something like a word cloud, and I put them in these 4 directions, 4 dimensions of, in principle, optimization, linear algebra, and probability theory and statistics, and machine learning algorithms. So I think we will go through this space in a kind of spiral way. So I would like to talk about different keywords in each session, and then hopefully later you can connect these dots together. Or maybe you can say, okay, this is not interesting, I like to look at it like this. It doesn't matter. So there are lots of keywords, so just think about it that you need to learn, and then you realize that you know it. So today I will talk about mainly probability theory and statistics. And for that, is it too small? Okay. I would like to start with the ideas of determinism and certainty, and then we will talk about these keywords like Laplace-Demond, Poincaré, and determinism, and deterministic unpredictability, and then this kind of stuff. And then we go to probability theory and statistics, and then I think I will try to show at the end what are, in principle, what are, in my opinion, limits of these things, or what are the benefits of each of them. But I think you need to know these terms, in my opinion, or maybe later you realize that maybe it was not necessary. So I will start with determinism. Determinism is, I would say, still is a kind of what the hardcore science is still, when we this is a kind of belief in objective truths, or finding some natural things in terms of mathematical equations. This is usually historically we can relate this to starting from 16th century after Descartes, and gradually we have this kind of Newtonian mechanics, and this is being celebrated from 16th century to almost end of 19th century in terms of equation-based science. So in principle, you're always interested in something if you find an equation about something. So in principle, we have these equations in Newtonian mechanics, and if one day if somebody's coming and say, okay, I have an equation how people walk, as we discussed last week, so this sounds scientific. So this is the idea of determinism, that you believe that there is some causalities in a deterministic ways that causes some kind of relations, and then at the end you have what you see. For example, gravity, and so on. Or when you push something and it moves, so you know that there is some causality. And then this was, like, I would say, the whole science for 300 years, and then they have this idea of, for example, this was the peak of that, I would say, Laplace-Demond, and it's an interesting topic, you can just check it out, that the idea is that Laplace said, if everything is based on this deterministic equation, if there is such a demon, or in principle a human, or God, or whatever, that knows all the equations, and if everything is based on causalities, so in principle we can say what is happening next and what is happening before. So there is everything is based on deterministic rules. So this was like a very disputed concept, because it looks very strong, and if you believe in this approach, then in principle you say, okay, there is definitely some rules how things are interacting, and then in principle we can simulate the reality in principle, because we can go back, because we say what was the elements that are caused this effect and this kind of phenomena and so on. But nevertheless it didn't work in principle, as you will see. But this kind of thinking in principle works in many things, and it's important to claim that it works. For example, I don't know, have you seen these videos of this person? Apparently he is a famous professor in machine learning, and he has these courses in I will stop this in science for high school students, and he talks about in principle determinism. And then, for example, in order to show how much he believes in this determinism, he makes this experiment with himself, and in principle, I just want to show you quickly, because you can check it later. I will put it online. He has this pendulum, and
this steel ball
maybe you can watch this.
And I'm going to stand with my back against this headrest, and in a moment I'm going to place it against my face. And then I'm going to let go.
So if you believe in equations, you know that it never hits, huh?
Theatre, and then it's going to swing back towards my face. Now, according to the laws of physics, it should stop just before it touches me. Okay, that's the theory. See what happens. I think this is probably worth a countdown, isn't it? Okay, are you ready? 3, 2, 1, go!
So this is really fascinating that we have these equations and then we can calculate them. But nevertheless, if you just add another one pendulum here, so you have a double pendulum problem, again you have equations and it's perfect. These equations are clean and it seems that it works. But nevertheless, if you simply visualize it or render it based on an initial starting point, it creates something completely different. And for example, this is one simulation that I made. And for example, let me run it again. Hello. So for example, if you start this double pendulum now, two pendulums and even each of them separately and together they make a system. So it's a system. Now you know the equations, and then everything looks interesting and similar to the previous example. But definitely, this is the patterns of the head of the second pendulum. So we have here kind of determinism, but it's unpredictable. And this kind of example started to be known by end of 19th century, is that you have deterministic systems, but you can't predict. And it depends a lot on the initial condition. So pragmatically, not theoretically, pragmatically, this Laplace demon doesn't work, because you don't know the initial condition. If you make a bit of mistake, then the patterns are completely different than what you expected. So this was a lot of work for, like, I think it started in 1880 by, for example, works of Poincaré and similar people like him. And then this was the starting point to criticize determinism. That from one point, sometimes even we have determinism, we can't predict, even with the equations. And sometimes, in many cases, we can't have these deterministic rules at all. This is mostly the discussion that we have last week. So, for example, another known example is this kind of bifurcation processes, that they are kind of chaotic process. Here we have very simple equation. We have a self-referential equation that y is y minus, for example, t minus 1 is y at time t is equal to y at time t to the power 2 minus c. And c is a fixed parameter. And interesting enough that here not related to the initial condition, but depending on these parameters, you have completely different patterns if you just change this parameter just a bit. For example, now here we just run this code, and then I show you what happens. So now we have a lot of traces of these y values for, let's say, for example, for 1,000 times, and then every time this only the c is changing, and everything is the same. And then you see the behavior of the values of y over, like for certain values you have these patterns, and then gradually you see these kind of patterns that they are all deterministic, but you can't easily predict. And if you just change the value of c by epsilon, very small epsilon, the pattern of y is completely different. So these are like main critics to this determinism in principle, and pragmatic critics to that, because we don't have such a measurement systems and such devices to be absolutely precise. So in principle we have always some kind of errors, and by these small errors we have problems always with prediction. And this is sometimes known as butterfly effect, for example, if you know that if there's a butterfly walking or flying somewhere, then you have a hurricane somewhere else in the world. So this is very known question in meteorology, for example. So then an interesting point is that in chaos theory, for example, there are people interested in working on these topics. For example, now if I visualize the value of y's over c, then you have this kind of interesting patterns that the values of y in this range is almost fixed, and then gradually you have two branches, and then you go further, you have two branches, and then there are many people who are studying actually this kind of phenomena in mathematics and physics, because they're very interesting in a way. It looks completely random, and then imagine now when you start observing a new phenomena, and then you don't know what is your parameter for your scenario, and then you might come up with a rule for that. You say, okay, this is my data and this is my conclusion, and so on and so on, but you don't know, for example, if the experimental setup was different, you were in a different, for example, curve. There are many of these kind of examples. Another case is Lorentz curves, which are very famous in this kind of double curves. And then the whole equation is this. The change of x over time is related to sigma is a scalar, y and x, and then y is related to x and y and z, and so on, and dz is related to x, y, and z. And all of these parameters are scalar, so they are not changing over time. Nevertheless, this is highly dependent on the initial condition. So, for example, you can run this code later. I just wrote it down here, and then you just calculate the path. Here we just, start with, 30 different starting points with very small differences, and the pattern is something like this. They're all in the same class of curves, and they are deterministic. So in the when you start with one initial point, this point, if it knows the equation, it knows that what happens to this point in time. But if you change a bit the starting point, there is no parameter here, just starting point, the pattern is totally different. So there are a lot of this kind of phenomena in the world, for example, weather and climate and these kind of things, and these are interesting to analyze, but at the same time it shows these limits of predictability. So I just want to show you that we have kind of deterministic patterns, deterministic systems, that they're unpredictable. So, for example, if you just visualize some of these traces of random starting points, you have this kind of data. So now we have, for example, you might think that, for example, in stock market, you might look at the behavior of these prices of different companies and so on. And there are many people who are trying to find equations, underlying equations. And then in principle, you can say, I know the equation of the system, but I can't predict, because you don't know what happens if the initial condition is a bit fluctuating. So this is somehow in between. So for me, this is still interesting mathematically, but in terms of application, it becomes in a way useless, because you just when you go to the application, you always deal with parameters and measurement and so on. So it's always not deterministic any longer, because you just don't know what are the parameters. So now you can think about it in different way. that now I would say this is, in my opinion, the starting point of probability theory. In principle, probability theory is older than this. Probability theory is at least starting from 15th century. But it gets more interesting from this time, early 20th century, because from this time we start working on populations. Now, for example, I showed you a population of patterns. Then you realize that there is a cluster of curves, right? Then you just realize that there are two centers, two attracting points, but they're every time is different. But you know that they are following the same kind of class. So this is usually the case with probability theory and statistics. We want to work with populations. For example, you know you have a dice or you have a coin. You know that always there is like either any side of this coin, or either you have one number from 1 to 6, but you don't know what comes out. So think about it. If you think about it like mechanically, you might model the movement of these dice. But and now it's easy that you simply say we don't do it because there is no need to do it, because you somehow accept that it's not possible to predict this. There are lots of factors affecting on this. So in principle, with probability theory, you somehow agree that you can't be deterministic about anything. Then you start playing with populations, or you are playing with the possible outcomes. So in the case of, for example, a dice or a coin, you are always trying to find out what would be your expected return, for example. If you are going to start a casino, you don't know how this casino would work. This, for example, these games that you are going to propose to people, but you expect that by average over time, you're always the winner. You're the winner, for example, by 55%, for example. So always you have 55% of gain. So this is the starting point of probability theory, maybe in a very not usual way, but I think it's good to know the background before probability theory as well. So there are many terms. From now on, I will try to just shoot you a lot of keywords, and then just we can talk about it later or now if you like. For example, first thing is that what is a variable, for example. I think for me, this is not a definition. A variable is a symbolization of a specific number, vector, matrix, or even a function, which takes a range of values. So variable is variable, so it varies, right? So it can be a matrix, it can be a vector. You don't need to always have a single number. So, but it's changing. So this is what you think it's changing. In this domain, what we have as parameter or constant is what we fix, or what is fixed during the course of, for example, experimentation. For example, when you say y equals 2x plus sine of x, here 2 is a parameter and x is a variable. Whereas, for example, in many different domains, you might think about a parameter as a variable. This is possible that it's interchangeable. And sometimes it's called features and this kind of things, or factors, for example. But most of the time when we talk about parameters, is a fixed or constant value within that domain of analysis. And then we have the idea of random variable. Random variable is a variable that takes a likelihood. For example, when you have a coin, either side of the coin have a likelihood. For example, if it's not a biased, the so-called unbiased coin, you think that the likelihood of each side is 50%. So the variable is either head or tail, or 0 and 1, but the likelihood is 50% in this case. If it's biased, then it's 60% to 40%. This is the meaning of random variable, that you have another likelihood on top of the possible value. So there's other factors and other terms. For example, I don't want to confuse you, but I think it's good if you're interested, go and read, just start with Wikipedia, for example. What is then difference between randomness and fuzziness and vagueness, for example? Randomness is when you don't know what is the outcome of your game, but fuzziness, for example, is if I ask you, am I tall or short? It's not about an outcome it's about your judgment, it's about your definitions. So this is the definition of fuzziness. So this is like vagueness or fuzziness, and then it goes to possibility theory, which is it's a research topic that I worked for like 5 years, but I don't recommend you any longer to go it's interesting to work. But for example, with machine learning, what we did with this fuzzy theory, I think you can do it better. We don't need this definition at all. So, but there are lots of axioms and theories and important principles. I just want to skip this because I think it will be too much. I'm just looking at your face, and then I think it's not that important as well. But just think about it quickly. Like these are the known as Kolmogorov axioms of probability theory, which was formalized, I think, early 20th century, if I'm not wrong. The first axiom, which is logical as well, it says that any event has a probability which is either 0 or larger than 0, and it's always less than 1. And the second axiom says sum of all the probabilities of all the events are 1. So it's either head or tail. So if you have two options, it becomes always 1. It becomes one of them possible. Third axiom says that, for example, probability of disjoint element is the sum of their individual probabilities. It's obvious, right? You just say it becomes either 1 or 0. It's either head or tail. It's either 1, 2, 3, 6, or like 1 to 6, for example. So you can just sum them if they're independent. And then you can say, for example, probability of empty set is 0. The probability of nothing happens, for example, it should happen. Some of these options should happen. So if you say the probability of nothing happens is 0. So these are like axioms, and it looks like more logical, but it's extremely helpful if you want to use them, for example. So another way to look at these things is in terms of Venn diagrams, which is I would say is a kind of set theoretical way. This is the whole area of possibilities, and this oval is A, condition A, and this is condition B. So this is called P, probability of A and not B. This is this region. So the area of this region over the whole region, this is the probability of A and not B. And this is, and I think it's not more than that. In all of these classification models in machine learning or statistical method, at the end is just summation and division, is nothing more. So if you get this, then everything is the same. Like these are the basics of, for example, Bayesian methods, for example, Bayesian networks and so on. And then you say the probability of A and B, of course, is an intersection of this. So the area of this area over the whole area is this probability, and so on. So you have always observations, and then you can calculate these kind of things. And then, for example, you have conditional probability, which says probability of A given B is probability of A and B given over probability of B. So this, you can think about it again, it logically makes sense. But they are helpful, and they're very extremely powerful, especially in Bayesian networks and Bayesian thinking in probability and statistics. I'll just skip it here, but I mean it's I think important that you just get familiar with these things. I'm not sure if you directly will use it, but if you know these terms, that they're helpful. So you can. This is a nice book. I recommend you, Sheldon Ross, First Course on Probability Theory. I read it before. I think it's a good book if one day you want to read this stuff. So I will skip this part. Then you have these notions of, as I told you, random variables. We always comes with a set of range of possibilities plus a likelihood over this possibility. So you have always a function over this range. So if your case is discrete, you call it probability mass function. If it's continuous, you call it probability density function. So here, for example, if you talk about this area, this is a continuous space. So you have a probability density function in principle. If you don't have a closed boundary, of course. So then I will go through these definitions. We have these definitions of, for example, like cumulative distribution functions, expected value, variance, and lots of known probability distributions. But I think you don't need to know by heart these equations. They are in principle useless, because we are using computers. In principle, you can use them easily. And here I just want to make a note that if you're, for example, all of these codes that I'm showing here are in Python. And if you're using in Python, definitely you should start using NumPy if you have not started yet. NumPy and SciPy and pandas, for example. And all of these equations, all of these values and terms are all embedded. So you can start generating random numbers and play with that. For example, if it says it's a coin, then you just say, okay, I assume that I have a coin. I generate a lot of experiments, and I want to check if the average values, for example, is 50% or not. So, for example, here we start with the binomial distribution. Binomial distribution says, imagine you play a game 10 times, and you want to know your expected number of success. For example, you toss a coin, for example, you flip it, and then you know what is your chance every time, but you want to know, for example, if you play 10 times, what is your chance? For example, if your chance of success is 20%, and if you're playing 10 times, you expect that by average you should win 2 times at least. If you play 1,000 times, and if you don't win 200 times, then you might check, okay, maybe this probability is wrong. So here, this is a binomial distribution. It's a simple equation, and then you just need to know this is the parameters. So you just say, this is the chance of my success, and that mean value that I expect is NP, which means like if you play 1,000 times, your chance is 20%, you expect to win 200, right? So, but you can run it here, for example. Now I can say, okay, go to NumPy, random, binomial, 10 times P. P is 20% or 0.2. And run it for 10,000 times. If you run it, it says average number of success in 1,000 times is 2 point something. So this is the way you can check the result, and you can play with these values. And what happens if you just change it to 8? Definitely it should be 8, right? And then here, this is the average number, the number of success you had in these games, in 10 games every time. You see that it has a distribution by the average, but the median value is 8. So this is the meaning of expected value. And the variance is the distribution of these values around the mean value. This is the notion of variance. And then if you visualize it like that, it says that by average, you see the peak is 8, and then you have the distribution of the errors. You can't be more than 10, for example, right? Because of that, you have this kind of skewness. So if you have geometric distribution, now it says geometric distribution is when we stop the game after the first win. So therefore, it's a measure of number of games that we need to stop the game. So you just say, I play as long as I'm losing. If I win the game, I stop. The game, you just say the probability is 3. What is your expected? Just play with that again. It's simple. And then you have different patterns. And it says, for example, you need to play at least 3 times out of 10 to quit the game, which is again logical, right? These are all the things. And then the whole idea of probability theory in principle is how to design systems. And in principle, in probability theory, mainly you're dealing with mechanism design. You're designing something that at the end the outcome is what you like, because you know that it's not deterministic any longer, but you just want to create a game. For example, at the end you are the winner. This is completely different than when you think about this game as a deterministic pattern. So if you have a uniform distribution, as it says, it's uniform. So this is when you have, for example, the values between 0 and 10, and then any of these values are possible. So it means that you have a very uniform likelihood for all of these values. So as you see, it's like random, completely random. So at the end it says, of course the average is 5 because it's between 0 and 10, but the distribution is like very uniform. Whereas the other one, you see that distributions are just more close to the mean, for example, right? So these are the things, and you just need to play with that, and it's extremely simple. It says NumPy, random, uniform, and then if you want to know what is inside, just say Shift Tab, and then I think there should be even the definition for this distribution. So if you just play with that, just get familiar with that. But most of the times you don't generate data. This is to be said as well. It's important to say. And most of the time we are working with the data. So we have already produced data. We do it backward in principle, and this is the starting point with statistics. So if you have normal distribution, and this is the definition of normal, for example, what we call normal. Now you play this game of normal, you expect to have something like this. And these are all the basics of the so-called scientific methods. Nowadays you have these papers that publish that they prove that this drug is effective or significant for this kind of disease. And the way they say significant, if you pass this kind of test. For example, if by average the number of people who are getting better is more than the number of people who are not getting better, it's always by an average. Then you just say this, for example, medicine is effective, for example. Then it's always a way to show that your way of doing research is as well scientific. But most of the time you can fake it as well. Yeah. I mean, it's important to know this because most of the time, in my opinion, unfortunately, there are many experiments that you can show that it's effective or it's not fake and so on, but it's not true. So then I think I tried to show you these examples, but then I told you as well that there's a difference between statistics now, and I want to tell you about this. Statistics and probability theory. In probability theory, you always assume that you have a function, like normal distribution, and then you expect what happens as an outcome. For example, you assume that you have a machine which is cutting this material like this, and then you know the expected tolerance or errors or precision, this kind of things. And then you want to look at, for example, measure the roughness of your material at the end, for example, surface roughness. So you expect to have a normal distribution around your, for example, error, for example. But in statistics, so in principle, you play with this, you try to design your machines in order to get acceptable results. In statistics, most of the time, it's opposite. You start with observations, and then you want to analyze these observations. You don't know this prior knowledge. You don't have this prior knowledge about the equations or the fundamental systems behind. So it's a kind of black box in principle. You don't know what is the machine which is producing this, but you expect that there should be a system behind, and then by data that you are observing, you try to identify that system. So this is the shift, in my opinion, from probability theory to statistics, and later, as we will see, to machine learning. Here, for example, we have two very important keywords or two concepts, I would say. One is a law of large numbers, and the other one is the central limit theorem. The law of large numbers simply says that if there is a system behind your phenomenon that you're observing, then if you play this for a long time, in principle infinite number of times, you get the expected mean value is exactly the mean value of the production systems behind. For example, if you don't know what is the probability of success in a coin, for example, it says that if you do it millions of times, what you get as the data-driven expected, not expected, just the average value. What you get as an average value is the true mean behind this. So, for example, I think Bernoulli has spent 20 years to prove this theoretically, but now again I think it sounds obvious for us because you say of course, but in that time it was not like that. So you need to mathematically prove that this is a fundamental thing for any system. So for example, we can play here. For example, we just say we want to flip a coin, and then we assume that there is a 50% chance. And then we just accumulate our belief about this mean value. For example, if I just flip it one time, and if it comes with head, then I say the probability. I need water. The probability of head is 1, and the probability of tail is 0. If you do it 2 times, so you just have two tails and 1 head, for example, then you say is again 1 and 0. If you do like 2 times head, 1 time tail, then you just have like 33% to 66. So this is the simulation of this law of large number. And as you see, it's interesting. We just play this game. I just say play with this game of 50%. I know it's 50%. I can change it later. And then draw random variables with this binomial distribution, which means that you have 2 outcomes with this chance of success. And then you just want to accumulate this average. And if you visualize it, it will tell you that it starts with 1. Thank you very much. It starts with 1, but over time, with 1,000 samples, you see that it's almost 50%. So now they proved it, and maybe I don't know. Maybe I'm not in a good direction, but I don't. For example, you might not see why it's important to prove this because it's so obvious. But it's important if you have with this background of determinism because you don't believe in these data-driven things. So you just want to know the equations. But here, in my opinion, this is the first law, the so-called law, and the first showcase of big data because in principle it says if you have a big data of about some measurements, you can trust the average. And if you increase the number of data set, it gets better. It never gets worse. So, for example, if we change it to 8, now you see, oops, okay, something is wrong. I think I should change it. Marker size. What is the value now? Okay, you should not believe in this. Average. Let me do it again. But maybe it's 2 already, or 8, no. So I think there's a problem, I'm not changing the values.
P is not used.
Pardon? P is not used? Ah. Oh, okay, it's MP random, thank you. Is it here or no? Okay, let's say it's P. Yeah. Okay. So this is in principle a theoretical proof for big data. So if you want to measure the average height of people, it's good to do it. But the problem is that most of the cases we are not dealing with like very simple measurable factors. So at the same time it loses its effectiveness. But anyway, it shows that if you have big data, you can trust the results. And if you add more data, it always gets better. This is very interesting, I think, if you think about it. So the other one is the central limit theorem, which is being used a lot in statistics and statistical tests, which says that the distribution of expected value of any random distribution turns to be normal distribution, which is very helpful because it says in principle you don't need to care about the underlying distribution behind your system that you're observing, but it proves that the mean value of this distribution follows the normal distribution. So in principle, this normal distribution has a lot of interesting properties that you can use it. For example, most of the statistical tests in any fields you can mention, they are based on this central limit theorem. So these two are really fundamental in statistics and most of scientific data-driven scientific discoveries. So now we are playing with that. Now imagine we want to run an experiment of this n times, which is 10,000 times, and then we want to use a Bernoulli, for example, distribution. We don't know what is the distribution behind, and every time that you run, I think the Bernoulli should be again 50%. Yeah, we define this Bernoulli here, which says 50%. I hope I'm not changing it here. Yeah, okay, we are using, let's change it to 2. This is our success gain. Now it says, even in principle, this is very strong because we know here the distribution, but in principle, for any observations or any measurement that you have, you don't need to know the measurement because it says if it's 20%, then if you run it for a long time, the average should be around 20%. And the average itself follows the normal distribution. So if you have two systems that you want to compare, in principle you can use all of these properties of normal distribution here. And this is interesting because it's unrelated to the distribution, underlying distribution, but it's only about the average of that phenomenon. So if you use uniform distribution again, it creates a normal distribution. So most of the cases we are dealing with a variance and average, and this is really helpful because it says whatever is the underlying systems which is producing this data, if you deal with the average, you can use this normal distribution. And as you can see here, still with this law of large numbers or central limit theorem or this distribution and so on, still we are in the struggle of this determinism, because still we want to say, okay, is it normal distribution or not? If it's normal distribution, is a kind of natural phenomena, and then we want to use all these properties of this normal distribution. And in principle, this is, I think, mainly the main problem and main challenge between, for example, people from statistics and machine learning and computer science, because in statistics and machine and probability theory, people always started with this background that I gave you, and in machine learning they just directly start with the data, and then they feed some models to the data, and they solve the problem, and then in principle they never ask this kind of questions. And they don't want to know a truth about underlying systems. For example, you just want to say, okay, if I'm producing a good translation in my automatic translation, or if I have a self-driving car, is it driving good or not? But you don't want to know if it's really representing the systems, underlying systems or not. So in principle, that's the problem, and in most of the cases now, for example, I have seen many times for example, in medical studies, they don't use these nonlinear models that hopefully in the next sessions we will talk. They always want to find simple and explainable rules. And it's not deterministic, but based on statistics and based on probability theory, but it still is explainable. For example, if you find a rational line, this is powerful because you can explain it. But if you say, I can drive, but I don't know how, this is what we discussed last week. People don't like it, for example. Here, statistics still wants to know why, and of course, it knows that deterministic system doesn't work. So this is the struggle I told you about. So I think I mentioned these things, but again, I repeat, like you need to know what is expected value, average, variance, median, mode, what is a box plot, if you want to play with the data. So, and all of them are already implemented. It's like if you use pandas, it's there. Just check with pandas, box plot, what is that? So you will learn how it works. And then you will learn this language, how you can communicate, how you can analyze the process. For example, if you have a lot of data sets, usually you start with these basic things. For example, you want to know if there's a direct correlationship between something. For example, I want to predict the price of houses. For example, this is a specific case that I'm working. The first thing is that you just plot them together. You see maybe there's a direct correlation between, for example, the location and the price. If it's the case, so you don't go further. You just say, okay, statistics here is enough. But usually it's not enough, and then you go further. So you need to know what is a histogram, for example, what does that mean? And histogram is a kind of empirical version of these probability density functions, for example. And then you need to know higher order statistics. You don't need to know this necessarily, but I can talk about it a bit because it's very interesting. Here is a connection between, for example, statistics and, for example, optimization, and then you will see that how they are connected, for example. So these are the topics of like what is mean or average, what is median, and what is the mode, for example. I don't know if you have heard about this before, but so here I just produced random data sets. Here is called beta function. If you don't know, it's fine, but here I think should be mentioned what was beta. Okay, we don't have it here, but is a distribution function. So it creates this kind of pattern. This is your data set. I create a histogram of that, and then the mode is the most frequent observation. So it's not necessarily fixed. Every time that you do if you have a new experiment, the mode is changing. So this is mode, and then you have the notion of median. Median is when you sort out your data sets, then the median value. I mean, if you count, like if you have 100, then number 50 or number 51, it depends in this case, is the median if you sort them. And the mode I told you, and the mean is exactly the average. So you have different kind of averages as well. So what does, for example, this mean means is interesting because if you can, there's a lot of interpretation for that from, for example, the point of view of energy functions and again physics, for example. The mean value is a result of an optimization problem, and then it's a place with the zero energy or minimum energy in principle, not zero. And here, for example, we have this notion of higher order statistics. Here what we do is that if this value is in principle 1, then in principle we are calculating the difference between all the points to this x bar, which is the mean value, right? We want to find this value. Then in principle, there is one point mathematically, in principle, that has the minimum value for this sum. You just simply say mean is, you just select one random point, and then you just calculate the distance of all the points to this point, and then you just calculate the sum, and then you just move this random abstract point. So mean is always abstract, median is concrete, because median is part of your observation, mode as well is part of your data set. And here I just visualize it, if it's it. Like you have these random points, by random I select this red point, which is not a part of your data, and then you see how this is the sum, and you see how if I move it, how this sum is changing. So the area that you have the minimum of these values, this is the definition of mean. And it's very interesting because later you will see that in linear regression, actually we find a line which has the minimum distance to all the points. So this is the linear regression, for example. And if you extend this, you go to higher order statistics, means that you use higher order momentums. For example, you will have different functions. For example, if you calculate this value and then put mean here, and then to the power 2, like a square value of this, and then sum them, this is the variance, for example. This is the expected distance to the mean. If you use the power momentum 3 or LP norm 3, then it shows you the skewness, whether the mean is on the right or the left side. These kind of things, and it's extremely interesting because you have, for example, you can find nice analogies for that. And then you will see that, for example, later when you want to train any model, including deep learning or whatever, at the end you have something like this. You want to find some parameters, and then you have some data set. And then you have always a kind of, it's called loss function there, that you want to minimize some kind of errors. If it's an average error, so you just use this simple norm. But you can add different kind of things. And then you just search in this space, and then these parameters, for example, in this case, is just one point in the space because it's a mean value. But sometimes in linear regression, as you will see, I think next week, is a line, a parameters of a line. So in principle, a linear regression, for example, like order of 2, for example, you have only 3 parameters. You put these parameters in this optimization, and actually the whole machine learning is like that. So these are all the connections. I think if you get familiar with these terms, you will see that later if somebody's using some kind of regularization, what does that mean, for example? So as I told you, we'll talk about this again in linear regression, and usually these are called loss functions, for example. And there again another term. I think I hope it's not confusing, but I'm just trying to bring these terms. There is another important term, or 2 terms. One is bias and the other one is variance. And if you want to visualize what does that mean, is that if you have this kind of goal, for example with these circles, in this case you are close to the goal, but you have high variance, means that you are not very precise. So you are shooting, but you have variations in your shooting, but you are not biased. Bias means here that you never shoot on the center. So this is the precision of your machine, that you can't be exactly to the point, but you know that you have a normal distribution, for example, that the mean is exactly the center of the point that you want to shoot. So here you have low bias, but you have high variance. But you can have low variance as well, which is the ideal case. And here, for example, you have high bias and high variance, and this is the worst case. And here, this is the case, for example, you are not, for example, your machine is not, for example, calibrated, for example. So you have bias, you're always shooting somewhere else, but with low variance. These are important terms because later, for example, when you're going to function approximation in machine learning, you always have training data, test data. You always get very good with training data and very bad with test data. So always is a trade-off between variance and bias and variance. So then I want to reach to what are in principle the limiting factors of statistics. As you will see that they are always trying to be explainable, right? So it's always limited to few factors. But in most of the real world problems, you have a lot of factors. And sometimes these factors are not meaningful necessarily. For example, if you're comparing two graphs, you don't want to know, for example, what is the effect of this node of this graph to the other nodes of the other graph. For example, you're looking for, I don't know, to compare two graphs that are representing two forms, for example. So in that case, you are going to more abstract comparisons and more complex, or in principle, more complex comparisons, which is a composition of several things. And in most of these cases, you will see that classical statistical methods doesn't work. For example, here, if you have three variables, this is a kind of scatter plot. This is, for example, x1 and x2, x1 and x3, and then correspondingly we have x2 and x3. And this is a very classical way that if you have some data set, you start with this to see maybe there are some patterns. When you have something like this means that in principle they are not correlated, right? You will say that they're like an intersection of two independent normal values. And then you have this, you will see that okay, maybe there is a function between x1 and x3. But the problem here I want to mention here is that, for example, there is no linear correlation. And simply all of these methods that they're talking about significant result, or if something is correlating with the other one, simply cannot solve this, because here a linear correlation says here there is no correlation because there is a nonlinear correlation. So simply, all of them are beautiful. It's important to use it, but forget it. So this is in principle the message, and you can play with that here. For example, now I have these three data sets. This is a pandas environment. It's like, think about it like an Excel file in Python, but it's beautiful and it has a lot of things. So you simply make these basic statistics. These are called usually basic statistics, and here it's called describe, for example, and then it says x1 counts. It is the same mean value of x1, mean value of, and then standard deviation, which is square root of variance, and the mean value of each of them. So these are the descriptive statistics that you usually calculate. And then you can calculate the covariance or correlations. And for example, here I wanted to show you that how you can do it manually. But in principle, I wrote this function, but you don't need to do it. Here is the case, for example, for NumPy. You just say correlation coefficients, and it tells you that, for example, x1 and x1 is correlating 100%. x1 and x2, almost no correlation. It's 0. And then it says x1 and x3, there is no correlation, which is not correct, because this function is looking only on linear correlation. Here is very clear, here is not clear. Like when you visualize it, you know that there is a correlation. But I mean, all of these beautiful equations are becoming in a way useless. So it says there is no correlation, which is not correct. So there are other methods that hopefully this is the starting point that what we can do here, for example. And in principle, in many applications, you try, as I said before in last session several times, you should try to convince yourself not to understand. And this is a bit tricky, because if you ask someone not to understand, they get angry. But here is exactly the point, because the statistics want to understand, it ends up with linear things, because when you have an argumentation is when it's linear. You can send the message linearly, right? It's very clear and it's explainable. And because of that, it's not complex any longer. So in most of the real world data-driven applications, you don't have such a thing. And then you should convince yourself, otherwise you're not part of this machine learning society, not to understand. Of course, I know many machine learning people don't say the same thing. They say, no, we understand, it's not correct, and so on. But I think this is the tricky part. And in comparison, as I said, in machine learning, we are interested in learning nonlinear patterns in action or in operation in principle. As I said, for example, as a very basic example, we have this field of econometrics. Classically, econometrics are a quantitative way of analysis, quantitative analysis of economic data. For example, think about it like real estate market or any type of market. In real estate market, econometrics at the end usually ends up with some coefficients and is a result of some kind of linear regression. And it says, for example, in this region, the effect of adding one room to the price is like this, for example, a single number. And because of that, it's very strong as a political argument. If you have this authority, for example, if you are the only person who has this data, and then you are the only person who is producing these reports, then you say, I know what is the effect of rooms to the price of the house. I know what is the effect of price of oil on the consumptions, or, for example, driving patterns and so on. And this looks very strong, but it's very wrong at the same time, because I have done this experiment in a real world data set, and you realize that no, it's not like that. There is no simple explainable coefficient. Whereas in machine learning, for example, we start to say, what if we can predict the price? We don't know the coefficients, but for any house, we can tell you what is the price, but we don't know why. We don't explain it, and that's the thing. Because of that, we have a cloud of all the possible whys. And this is I think the limits of statistics in principle. Nevertheless, it's very helpful. You need to know these techniques, but for me, for example, this was like one session on the statistics, and I think I try to convince you that why it has these fundamental limits. So as we will see later in next sessions, for example, we will talk about these nonlinear techniques, and for example, we will talk about density learning instead of using a known density function. For example, if your data is like this, which kind of distribution you would fit here? Because all of these data sets so far we had was like that, and then like this, and then even central limit theorem, which was one-dimensional, you said, okay, it looks cool because it creates this kind of normal distribution, but in most of the real cases we have these kind of patterns. So there is no specific, like here is like a two-dimensional data set, but you don't have one. So in principle, one person could say that, for example, here I cut this space, I fit one normal distribution here, one normal distribution here, one normal distribution here, and so on. So this is when you go to non-parametric methods, for example. And then this is when you start with learning the densities. So this will be the next week. For example, you can fit models to that, and which are a combination of statistics and machine learning. It's not that much of machine learning yet, but it's interesting because you learn this distribution, which is not a classical idealized form. But by that, you can generate new data, you can randomize, and you can create synthetic data set and so on. And then you can cluster this data set and many other things. And for example, this example for me is very clear, and hopefully we will talk about this in the next week. So it was, I think, as I told you, it was not very linear. It was because I couldn't manage to put it in like very straight line, but I tried to put a lot of keywords and show you a lot of keywords. I hope some of them were interesting for you. But again, just for playing, because we are talking about data-driven modeling, if you want to, because I told you a certain story, I said from 16th century we had this idea of determinism, and later we had end of determinism, and then we had probability theory, statistics, and so on and so on. So now we have a kind of a data-driven way to check if we are right or not. So there is a project, maybe you know, it's called Google Ngram. In Google Ngram, in principle, they scanned, I think, billions of books from 1800 up to 2010. So they just count number of keywords, or Ngram. Ngram means, for example, when it's 1 gram is like one word. When it's 2 gram is like two words together. N means like N, right? You just say 3 grams, 4 grams, and so on. So here we want to check, for example, what if our story was correct or not. So I have 3 keywords: probability, statistics, and machine learning. And then if you visualize this, you will have something. Maybe I should have known these patterns. This is a normalized frequency of these keywords in all of these 10 billion books, or 5 billion books. I don't know if I'm not wrong. So you will see that this is, I call it some kind of life cycle of these concepts. This line shows the popularity of probability theory. As I told you, it's before 1800. but it goes down for a while. And then again, I think this is a starting point of computation, and I think quantum physics, again, it gets popular, but it's like somehow solid after 1970s, 80s. And after that, it's not that much popular, it goes down. Nevertheless, it's a backbone of machine learning, but it's not any longer like producing new things. And if you look at, for example, this one, I told you what, now this is statistics, you will see that this break-even point, something like that, that you have this in these times that I told you, this was like end of determinism, and this is like the starting points of statistics and the statistical methods that you just give up to play with the equation. You just say, let's start with the populations instead of equations. So this is the beginning of statistics, and it grows up and it goes down, and then definitely you had no machine learning before, and then gradually started in let's say 1980s, and it's still going up. So seems that this story, I think for me, was like kind of how to say, double check. You can play with this. This data is available, for example, for free. Now you have this code, you can run it. This data is calling an API from Google Ngram. You can check, for example, this is a data-driven way of checking topics, for example. For example, if you want to check any topics, there's another version which is Google, what is it? Google, the other one which is faster, like a recent Google Ngram, Google Trends. So Google Trends is starting on a daily basis, for example. On a daily basis, it counts number of keywords, for example. So this is very interesting as well. Even you can do a lot of prediction by that. It has been shown. So this is the story. I think for me, this was like one session on these guys, statistics and probability theory. Most likely we will talk about them again, but the focus of the next sessions will be only on this machine learning part. And then in each session, we will talk about different problems that it's not possible to address by the previous types of models. So including clustering, what are the categories of machine learning, unsupervised learning, supervised learning, reinforcement learning, or this kind of, which is very helpful in its robotic environments and game environments, and lots of algorithms. And then we talk about very powerful methods that nowadays it's very famous, like deep neural networks, like convolutional neural networks, and LSTM. For example, with LSTM or recurrent neural networks, I show you that you can learn the underlying functions of this Lorentz curve. You can't predict exactly the same pattern, but you can generate meaningful patterns. For example, like here, we will see this. I did this like before. You can start with initial point and think about it like a time series prediction. And it was interesting because it's been shown that this recurrent neural networks learns the underlying dynamics without any explicit equations. But then, since it's a chaotic process, you can't follow exactly the same path, but it learns it in a probabilistic way, but at the end it creates the same patterns. And these are all very interesting, and then they have a lot of applications in different dynamical systems, for example. So for me, I think this was end of this session. I hope you like it, and yeah, and let me know if you have questions, and yeah, if you have other topics that would be interesting, we can bring it and discuss it, or if you have any other projects or papers, even we can talk about it. I would be very happy if you have these kind of interactions, or if you would like to present as well. This would be very interesting as well. And at the same time, trying to contact some people that I know to invite them. For example, some people that I know, they are working with graphical data sets and graphs and machine learning. This is not that much developed compared to the others, but I know that there are a lot of applications in like architectural design which you are dealing with the graphs. So this would be hopefully this one of the sessions. So no questions? No.